Lieutenant Yuri Maslov sits in the nose of a 400-ton machine skimming 15 feet above the Caspian Sea at 280 miles per hour. 8 jet engines screaming behind him, watching the radar altimeter because dropping 3 feet means the hull strikes a wave and the entire crew dies in the next 4 seconds. The stubby wing overhead generates lift only because compressed air cushions between metal and water, a physics regime no conventional aircraft depends on. Climb too high and the cushion vanishes. Descend too low and the fuselage hits a wave crest at highway speed. Maslov holds the yoke with both hands, eyes locked on the altimeter needle, because this machine flies in a corridor measured in feet, not thousands of feet, and there is no margin for error.
Maslov advances 8 throttles to full power and 28,000 pounds of thrust per Kuznetsov. Turbofan spools up in 4 seconds. The engines sit in a cluster on the vertical tail, mounted high to keep the intakes clear of saltwater spray. Each turbine drinks fuel at 1,100 pounds per hour, and all 8 must run continuously because there is no glide capability, no backup lift if the power fails. The throttle bank is a wall of black levers under his left hand, and every one must stay forward or the air cushion collapses and the machine becomes a 400-ton brick with no options. The 240-foot wide craft accelerates to 180 miles per hour, and compressed air begins forming a cushion between the stubby wing and the water surface. At 220 miles per hour, the bow lifts. Maslov holds the yoke neutral and watches the radar altimeter settle at 15 feet, inside the ground effect envelope. The ride smooths as the air thickens beneath the wing, pressure building between metal and water, like a hydraulic jack that supports weight without touching the surface. Speed and altitude lock together now. Below 220 miles per hour, the cushion cannot hold the weight, and above 50 feet, it dissolves entirely. The air cushion thickens and lift increases to support 400 tons on a wing designed for 1/3 that load in free air. Maslov trims for level flight. Fuel flow reads 9,000 pounds per hour across 8 engines, enough for 90 minutes at cruise speed. This is not aerodynamic lift from airflow over the wing. This is brute force compression of air trapped between wing and water, a regime that works only because the surface beneath him is flat and endless. Over land, the cushion would vanish instantly because terrain breaks the seal. The co-pilot logs airspeed, altitude, and engine temperatures. This is the 7th test flight this month, and the profile is identical to the previous 6. Each sortie validates the same narrow parameters. Maintain 15 feet, plus or minus 3 feet. Hold 280 miles per hour, plus or minus 10, and return before fuel drops below reserve. The crew has flown this corridor so many times the numbers feel routine. But routine is built on margins that remain razor thin. One engine failure or one navigation error converts a test mission into an emergency in seconds. Behind the cockpit, a weapons officer monitors 6 Mosket anti-ship missiles mounted in launch tubes along the dorsal spine. Each missile weighs 9,000 pounds and carries a 660-pound warhead designed to punch through the hull of a cruiser at Mach 2.5. Payload capacity that no conventional seaplane could carry and no surface vessel could deliver at 300 miles per hour. The Ekranoplan is not a transport or a reconnaissance platform. It is a strike weapon, built to close on a carrier group too fast for interception and launch before defensive systems acquire a lock. The flight plan calls for 2 hours at 15 feet, a practice missile lock on a decommissioned destroyer hull, then return to the Naval Air Station on the northern shore. The route is a 120-mile loop over open water, where wave height averages 3 feet, and air traffic is non-existent. Maslov will approach the target hull from the west, the weapons officer will initiate simulated launch sequencing, and the craft will brake left and return to base. Standard profile, standard conditions, standard outcome expected. The crew has done this before and will do it again next week. Maslov scans the engine instruments one more time. 8 exhaust gas temperature gauges sit at 850 degrees Celsius, 8 fuel flow needles hold steady, and all 8 oil pressure readings are green. The machine is operating within limits, and the margins that looked tight on the first flight now feel almost comfortable. 30 minutes into the sortie, fuel remaining is 63 minutes at current burn rate. The co-pilot updates the navigation fix and confirms they are on course. Everything is nominal. And nominal is exactly where the crew expects to stay for the next 90 minutes.
Maslov receives clearance to climb to 60 feet for a sensor test. The flight plan calls for a brief altitude excursion to verify radar cross-section at higher altitude, a data point the engineers need for threat modeling. He pulls back on the yoke and the nose rises 3 degrees. Airspeed holds at 280 miles per hour and thrust remains at 98%. The radar altimeter climbs through 20 feet, then 30, then 40. The ride is smooth and the engines are steady, but the vertical speed indicator begins drifting downward, even though the nose is still high. The radar altimeter climbs through 50 feet and lift falls by 60% in 8 seconds. The airspeed indicator still shows 275 miles per hour, but the vertical speed indicator swings to minus 800 feet per minute. The air cushion between wing and water has thinned to nothing, and the stubby wing cannot generate enough aerodynamic lift to support 400 tons in free air. The nose is high, the engines are screaming, and the aircraft is descending like a grand piano dropped from a crane. Maslov shoves the throttles forward, but they are already at 98% power and cannot produce more thrust without overtemping the turbines. Maslov shoves the yoke forward and drops the nose. The altimeter descends back through 40 feet, then 30, then 20. At 15 feet, the compressed air cushion reforms beneath the wing, pressure builds, and lift returns. The descent stops and the aircraft levels off. The entire excursion lasted 18 seconds. The co-pilot's hands are locked on the edge of the instrument panel. Maslov calls out the recovery altitude and trims the yoke neutral. Above 50 feet, this machine does not fly. It falls with style until it re-enters the cushion or hits the water. The co-pilot notes the altitude excursion in the log. Above 50 feet, the wing cannot support the aircraft's weight. The Ekranoplan is not a plane that can climb. Maslov radios the flight engineer on the ground and reports the sensor test aborted due to loss of lift. The engineer replies that climbing out of ground effect at this weight requires either 18 more tons of thrust or a wing twice the current area, and neither is available. The design is not incomplete. The design is optimized for one flight regime, and that regime has a ceiling measured in feet, not thousands of feet. The constraint is absolute. Flight below 3 feet risks hull strike. Flight above 50 feet guarantees loss of lift. The 47-foot window between them is the only regime where the machine survives. Inside that window, the air cushion supports weight the wing cannot carry alone. Outside that window, the laws of aerodynamics reassert themselves, and the wing area is inadequate, the thrust insufficient, and the outcome inevitable. Maslov has just learned that the altitude envelope is not a guideline. It is a physics cage with walls made of compression ratios and lift coefficients. Airspeed is equally unforgiving. Below 220 miles per hour, the cushion collapses entirely because dynamic pressure drops below the threshold needed to compress air beneath the wing. Below 180 miles per hour, the bow strikes water and the vehicle cartwheels. Maslov must keep the throttles advanced and the engines healthy because decelerating is not an option unless he is over a runway. And there are no runways on the Caspian Sea. Speed and altitude are handcuffed together. Lose one, and the other becomes meaningless. Conventional aircraft can glide if engines fail. The Ekranoplan cannot. The wing generates lift only inside the ground effect cushion, and the cushion exists only at speed. If the engines quit, airspeed decays, the cushion collapses, and the hull impacts water within 12 seconds. There are no ejection seats because the aircraft flies too low for parachutes to deploy. The crew's survival depends entirely on 8 turbines continuing to run. And turbines are machines that occasionally fail. Maslov now understands that every minute in the air is a minute without backup options. Maslov resumes the standard profile at 15 feet and 280 miles per hour. The instruments read the same as they did 20 minutes ago, but the margins that felt comfortable now feel like tightrope wire. The altitude band is 47 feet wide, but practical flying tolerance is plus or minus 3 feet because wave height and turbulence eat the rest. The speed margin above stall is 60 miles per hour, but losing one engine cuts that to 30. What looked like buffer has evaporated into fragility, and the crew now knows that nominal performance is built on physics that will not negotiate. 40 minutes into the flight, engine number 6 surges. Exhaust gas temperature spikes to 1100 degrees Celsius, and the compressor stalls. The turbine blades are losing material to metal fatigue, and the airflow through the engine is no longer smooth. Maslov sees the temperature needle spike into the red zone and hears the change in engine tone, a roughness that means the compressor is no longer producing thrust. He retards throttle 6 to idle, and the engine spools down. Thrust drops by 28,000 pounds, 1/8 of total power gone in 3 seconds. Airspeed begins to cane. 280 miles per hour, then 275, then 270. The air cushion pressure decreases as dynamic pressure falls, and the craft settles lower toward the wave tops. The radar altimeter reads 14 feet, then 13. Maslov can feel the change in ride quality, a slight roughness as the hull gets closer to the water surface and turbulence starts affecting the cushion. The co-pilot calls out the critical speed threshold. Below 220 miles per hour, the cushion collapses entirely. Below 180, the bow strikes water and the vehicle cartwheels. They have 50 miles per hour of margin, and it is disappearing at 5 miles per hour every 10 seconds. Maslov advances the remaining 7 throttles to emergency power. Turbine temperatures climb into the red zone, but airspeed stabilizes at 265 miles per hour, 15 miles per hour above the buffer. The engines are now running beyond continuous limits, consuming metal life with every minute at this setting. Fuel flow jumps to 11,000 pounds per hour across the 7 remaining engines. The flight engineer calculates 48 minutes of fuel remaining at this burn rate, not enough to reach the Naval Air Station 90 miles west. Maslov has bought speed at the cost of endurance, and the math does not balance. Maslov must choose: continue west and ditch in open water when fuel runs out, or divert south to the nearest shore 30 miles away and risk a landing on an unimproved beach. Ditching at 260 miles per hour in open water means the hull breaks apart on impact and the crew has no time to evacuate. Landing on a beach means threading a narrow corridor between offshore rocks and dunes, then hoping the sand is firm enough to stop 400 tons without the gear collapsing. Neither option is safe, but one offers a chance. Maslov banks 2 degrees south. The wingtip drops to 11 feet above the water, and the right stabilizer trailing edge throws spray. Any more bank, and the wing strikes a wave and shears off. The 240-foot wingspan leaves only 120 feet of clearance per side at safe altitude, and Maslov is flying inside that margin now. He holds the bank angle at 2 degrees and watches the compass swing south. The turn radius is over 2 miles because turning tighter means banking steeper, and banking steeper means dying instantly. The beach is 30 miles away, and every mile closer reduces options because there is no aborting this divert once fuel drops below 20 minutes. Fuel remaining is now 36 minutes at emergency power burn. The co-pilot updates the navigation fix. 24 miles to the beach, arrival in 6 minutes at current speed. That leaves 30 minutes of fuel on the ground if everything goes perfectly, which means 0 margin for a go-around or a second approach. Maslov will get 1 chance to plant the hull on sand, and if the beach is too soft or the approach angle is wrong, the landing gear will collapse and the fuselage will cartwheel through the surf zone, tearing itself apart and igniting the remaining fuel. 1 chance, 6 minutes away. Maslov crosses the commitment point.
Fuel is now below 20 minutes, and there is no returning to the Naval Air Station. The shore is visible ahead, a tan line beneath gray sky. The beach runs north-south for 15 miles, but only a half-mile stretch is clear of rocks and debris. The weapons officer in the back radios the base and reports emergency landing imminent, requests crash and rescue to stand by, but the nearest helicopter is 40 minutes away. The crew is alone now, committed to a landing that no Ekranoplan pilot has ever practiced, because there is no simulator and no procedure for beach landings at 230 miles per hour. Ground effect occurs when a wing flies within one wingspan of the surface. The downward airflow cannot escape and compresses into a high-pressure cushion beneath the wing. The cushion reduces induced drag by 40% and increases lift coefficient by up to 50%, effectively giving the wing more area without adding structure. For conventional aircraft, ground effect is a brief phenomenon during takeoff and landing. For the Ekranoplan, ground effect is the only flight regime that exists. The wing is sized for ground effect lift, not free air lift, and leaving that regime means leaving the sky. Lift formula: L equals 1/2 times air density times velocity squared times wing area times lift coefficient. Ground effect multiplies the coefficient, allowing a smaller wing to carry more weight. The Lun-class wing has 800 square meters of area. In free flight at 280 miles per hour, that generates 180 tons of lift, less than half the aircraft's 400-ton weight. Inside ground effect at 15 feet, the lift coefficient increases from 0.6 to 0.9. The same wing now generates 420 tons of lift, enough to support the airframe with margin. Every number in the equation matters, and none of them negotiate. Altitude to chord ratio governs the effect. Below 0.1, roughly 10 feet for this wing, pressure spikes, but wave strike risk becomes unacceptable. Above 0.3, roughly 50 feet, the cushion dissipates and lift drops 80%. The sweet spot is 0.2, about 15 feet above the surface, where the cushion is strong enough to support weight, but the hull clears waves with margin. This ratio is not a design choice. It is a physics constraint derived from how far compressed air can spread before it escapes horizontally. Maslov flies at 15 feet because that is where the equation balances, not because it feels comfortable. Speed governs cushion pressure. Below 220 miles per hour, dynamic pressure falls below 180 pounds per square foot, and the cushion cannot support the weight. The aircraft descends until the hull contacts water. Dynamic pressure is 1/2 times air density times velocity squared. It rises with the square of speed, which means small speed losses cause large pressure drops. Losing 10% of airspeed cuts cushion pressure by 19%. At 400 tons, there is no reserve. The cushion must produce full pressure continuously, or the aircraft falls. Airspeed is not a performance target. It is a survival threshold enforced every second. Losing one engine cuts thrust by 12.5%. At maximum weight, that drops equilibrium speed to 250 miles per hour, only 30 miles per hour above the cushion collapse threshold. There is zero margin for turbulence or pilot error. Losing two engines drops speed below 220 miles per hour within 40 seconds unless weight is reduced immediately. The Ekranoplan carries no droppable payload except fuel, and dumping fuel below reserve means the aircraft cannot reach shore. Every engine must run. Every turbine must hold together, or the crew faces a forced landing measured in seconds, not minutes. The wing is small because ground effect allows it to be small. A conventional wing sized to lift 400 tons in free air would span over 400 feet and weigh 60 additional tons, requiring 12 engines instead of 8, and consuming fuel so fast the range would drop below 200 miles. The Lun design trades altitude capability for payload and speed. The engineers did not fail to build a climbing wing. They deliberately built a non-climbing wing because the mission profile, striking carrier groups at wave-top height, never requires altitude. The constraint is intentional, and accepting it unlocks performance no conventional aircraft can match. Maslov descends to 12 feet to maximize lift coefficient and stretch fuel range. The radar altimeter tolerance is now plus or minus 1 foot. The shore is 3 miles ahead, and the beach is visible between scattered rocks. The co-pilot identifies the clear approach corridor, 0.6 miles wide, oriented northwest-southeast, with offshore rocks 200 feet to the south and dunes 150 feet to the north. Maslov will have 12 seconds from crossing the beach threshold to throttling back and touching down. If the hull strikes a rock, the fuselage splits open. If he overshoots the clear zone, the landing gear digs into soft dune sand and the aircraft tumbles. A squall line appears on the weather radar 10 miles ahead. Surface winds gust to 35 knots and wave height builds to 6 feet, twice the safe clearance margin. The storm is moving east at 15 miles per hour, directly across the approach path. The co-pilot calculates the divert. Turning east adds 12 miles and 8 minutes of fuel burn. The tanks will run dry 4 minutes before reaching the alternate beach. Maslov holds course into the squall. The only path to survivable landing goes through the weather, and there is no fuel to go around it. Maslov holds course into the squall. Airspeed fluctuates between 255 and 270 miles per hour as gusts hit the fuselage, and the altimeter swings between 10 and 14 feet. Rain hammers the windscreen, and visibility drops to a quarter mile. A wave crest rises to 8 feet. The hull clears it by 4 feet, and the pressure spike beneath the wing momentarily adds lift, then vanishes as the trough follows. The radar altimeter is now the only reliable reference because the horizon is gone and the water surface is a chaos of white spray and gray shadow. Maslov flies the numbers because there is nothing else to fly. Engine number 3 compressor stalls from ingesting spray. Maslov retards throttle 3 to idle. 2 engines now offline, thrust down 25%. Airspeed decaying through 245 miles per hour. The cushion begins collapsing. Descent rate climbs to 200 feet per minute, and the bow drops toward the wave tops. Impact in 15 seconds at current rate. The co-pilot calls out the altitude, 11 feet, then 10, then 9. Maslov has no altitude to trade and no power reserve left. The remaining 6 engines are already at emergency limits. The only option is to reduce weight or accept water impact within the next heartbeat. Maslov firewalls the remaining 6 throttles and dumps 2,000 pounds of fuel to reduce weight. Fuel streams from the wing vents and evaporates in the engine exhaust. The aircraft is now 5% lighter, and the cushion pressure requirement drops proportionally. Airspeed stabilizes at 235 miles per hour, 8 miles per hour above stall. The descent stops, and the altimeter holds at 9 feet. Fuel remaining is now 12 minutes, barely enough to reach the beach and stop. The shore breaks through the rain 2 miles ahead. Maslov has traded endurance for survival, and the trade leaves no margin for error or delay. Maslov crosses the beach threshold at 230 miles per hour and 10 feet. The squall is behind him now, and visibility clears to half a mile. The sand is tan and wet, firm enough to support weight, but soft enough to grip if the hull digs in. He retards all 6 throttles to idle, and the engines spool down. The nose drops, and the air cushion collapses as speed falls below 220 miles per hour. The main gear strikes sand at 180 miles per hour, and the hull settles onto the beach, plowing a trench as friction converts speed into heat and spray. The world is noise and sand and deceleration. The hull plows a 600-foot trench before stopping. Sand sprays over the cockpit and the windscreen goes dark. The engines wind down to silence, and the airframe settles with a groan of stressed metal. Maslov cuts all electrical power, and the instruments go black. The co-pilot unstraps and pops the nose hatch. Daylight floods in, and the crew evacuates through the hatch, dropping onto wet sand. The hull is intact. The landing gear is collapsed, but the fuselage shows no cracks. Fuel remaining is 340 pounds. 90 seconds of flight time at the burn rate when they touch down.
Maslov looks back at the trench and realizes they stopped 80 feet short of the dune line. Investigation determines Engine 6 failed due to turbine blade fatigue. Engine 3 failed due to saltwater ingestion in rough air. Both failure modes were predicted, but deemed acceptable risk for the test program. The Lun-class power plant was designed for 500-hour turbine life between overhauls, but operating in saltwater spray and ground effect turbulence reduced that to 300 hours. The test sortie was hour 287 for Engine 6. Acceptable risk is still risk, and on this flight, the acceptable became actual. The crew survived because Maslov made the correct decision in the correct sequence within margins measured in feet and seconds. At the National Photographic Interpretation Center in Washington, analyst Karen Frost reviews satellite imagery of the Caspian Sea, a 400-ton object moving at 300 miles per hour, altitude 15 feet, no wake pattern matching any known ship. The imagery was captured 8 months earlier during a routine reconnaissance pass. Frost's classification matrix has no box for this. Too fast for surface vessels, too low for aircraft, too heavy for helicopters. She tags it Unidentified Maritime Contact and flags it for senior review. The object appears on 6 more passes over the next 3 months, always at the same altitude and speed, always over water. CIA analysts spent 6 months building a new vehicle category. The Ekranoplan does not appear in ship databases because it moves 3 times faster than the fastest hydrofoil. It does not appear in aircraft threat libraries because it cannot climb above 50 feet or maneuver like a jet. Existing doctrine assumes surface threats move at ship speeds and air threats operate above 500 feet. The Ekranoplan occupies the gap between them, a regime where surface radar loses track intermittently, and airborne radar sees ground clutter, not aircraft. The vehicle is not invisible. It is uncategorizable, and that is more dangerous. NATO rewrites engagement doctrine to address ground effect vehicles. Surface ships cannot engage targets moving faster than 250 miles per hour because gun tracking systems assume slower closure rates. Fighter aircraft cannot engage targets below 100 feet without risking ground collision during attack runs. The Ekranoplan sits in the gap, immune to both threat layers unless someone invents a new weapon system or tactic. NATO assigns it the reporting name Utka, Russian for duck, but never develops effective countermeasures because building a ship fast enough or an aircraft low enough would cost more than the Soviets spent building the original threat. The Soviet Navy operates the Lun-class for 15 years, primarily as a missile strike platform in the Caspian and Black Sea. The operational record is sparse, but indicates roughly 400 sorties over the service life. The vehicle never engages a real target. It flies training profiles, intimidates NATO reconnaissance aircraft by appearing on radar at impossible altitudes, and serves as a psychological weapon by existing. The mission profile, closing on carrier groups at 300 miles per hour and launching 6 anti-ship missiles before defensive systems acquire lock, remains theoretical because the Cold War does not escalate to shooting. The vehicle works exactly as designed, within its constraints, and never proves itself in combat. The program ends in 2001, when the hull corrodes beyond repair and funding evaporates. Saltwater spray and ground effect turbulence accelerate corrosion in ways the designers did not fully predict. The airframe requires 12,000 hours of maintenance per 1,000 flight hours, and post-Soviet budgets cannot support that ratio. One airframe survives in a naval museum in Dagestan, beached permanently on the shore of the Caspian Sea. The vehicle sits on sand, engines removed, missile tubes empty. A monument to a weapon system that worked exactly as designed, but became obsolete when the strategic competition it was built for dissolved. The Ekranoplan forced both superpowers to create a new vehicle category for a single platform. NATO doctrine still includes ground effect vehicle engagement protocols, though no such vehicles remain in active service anywhere in the world. The physics that made the Lun-class possible, ground effect lift,
remains the same. But the operational constraints, zero altitude margin and no climb capability, remain unacceptable for modern military missions that require flexibility and survivability. The category exists in doctrine, but not in reality. A legacy of the moment when one nation optimized a design so tightly to a single mission that it became simultaneously brilliant and extinct. Karen Frost's original assessment, unidentified maritime contact, was correct. The Ekranoplan was unidentifiable because it violated every assumption built into ship and aircraft databases. It moved like a jet, but could not climb. It carried missiles like a cruiser, but operated alone. It appeared and disappeared from radar because altitude and sea clutter created blind zones no conventional platform exploited. The confusion was not incompetence. It was the predictable result of encountering a vehicle optimized for a regime no one else considered buildable or survivable. The Ekranoplan terrified analysts not because it was invisible, but because it was visible in a way that made no sense. The myth is that the Ekranoplan was a failed Soviet experiment, a white elephant that proved impractical and was quietly abandoned. The reality is that it was an operational missile platform that worked within its design envelope and forced NATO to create entirely new threat categories because existing doctrine had no box for a 400-ton craft that flew at ship altitude with aircraft speed. It failed not because the design was flawed, but because the strategic competition it was built for ended, and no peacetime mission justifies the operational cost of flying a vehicle with 47 feet of altitude margin and zero engine-out glide capability. Impractical, yes. Failed, no. Ground effect physics remains available to any designer willing to accept the constraints. The lift coefficient increase, the drag reduction, and the speed potential are still there, waiting in the equations. But the altitude cage and the speed floor remain non-negotiable, and modern military doctrine prioritizes flexibility and multi-role capability over extreme optimization for a single profile. The Ekranoplan was the logical conclusion of ground effect exploitation, and the fact that no one has built another one in 25 years suggests that the conclusion, while technically valid, is operationally terminal. The physics works. The mission does not. Maslov flew the Ekranoplan for another 18 months after the emergency landing, logging 73 more sorties within the same 47-foot altitude envelope. He later described the aircraft as the most capable platform he ever flew, and the most unforgiving. Capability and margin are not the same thing, and the Ekranoplan maximized the former by eliminating the latter. Every sortie was flown inside a physics cage that permitted no mistakes, no equipment failures, and no bad weather, unless you were willing to die. The lesson is not that the design was wrong. The lesson is that extreme optimization extracts a price, and the price is paid in blood when the margins vanish. The sea monster CIA satellite saw moving at 300 miles per hour over the Caspian was not a hallucination or a sensor error. It was a weapon system that made perfect sense within the constraints its designers accepted, and no sense at all within the categories its observers used. It flew because ground effect physics permitted it, and it terrified because classification systems did not account for it. The Ekranoplan was never mysterious. It was simply optimized for a regime so extreme that everyone else assumed it was impossible. Maslov proved it was possible. The corroded hull in Dagestan proves it was also unsustainable. Both truths are correct, and the vehicle remains the only example of a category built for one.